Have you ever noticed how your phone battery seems to, I don't know, run down faster when it's really cold out? Or maybe why a shiny new car eventually gets those telltale orange spots and rust?
Yeah, or even that tiny spark in your car's engine. How does that ignite such a powerful reaction?
Exactly. These things aren't just random quirks, are they? They're actually all examples of this, well, hidden, incredible dance of electrons happening constantly all around us.
That's exactly right. And welcome everyone to the deep dive into electrochemistry. It's really the field that explains how chemical reactions can either generate electrical energy or be driven by it.
Yeah, we're going to sort of pull back the curtain today on these surprising connections, hopefully turn some everyday mysteries into, clear insights.
Our mission today is to really unpack how this electron transfer underpins so much from the power in your pocket to making materials on an industrial scale.
And we've got a good stack of sources for this dive detailed textbook chapters, lecture slides, they'll be our guide. So yeah, get ready to maybe see the world a little differently.
Okay, so to really grasp how this invisible dance of electrons creates energy or is driven by it, we have to start with the basics, the fundamental choreography, redox reactions.
Redox, right? Reduction oxidation.
Exactly. It just describes any chemical process where atoms change their, let's say, ownership of electrons. One species loses electrons, that's oxidation.
Okay.
And another one gains them, that's reduction. And the key is they always happen together. You can't have one without the other.
So it's not just about like what atoms are there, but how their electron balance actually shifts during the reaction.
Yeah, precisely. And this electron exchange is absolutely fundamental. It tells us exactly how much energy is being transferred in a chemical system. The trick, though, is accounting for every single electron, especially when balancing these reactions in a way that really reflects that energy flow. It's not just about balancing atoms anymore.
Right, you have to balance the charge too.
That's where the half reaction method comes in. It's really invaluable. It's our systematic way to track those electrons step by step.
I definitely remember wrestling with these in chemistry class. It felt a bit like a puzzle. But the aha moment, like you said, is understanding why you're doing it to quantify that invisible flow.
Exactly.
So maybe walk us through a classic example, not like every single step like a recipe, but hitting the main ideas. Our sources use ions reacting with dichromate. Fe2 plus Cr2O72 lead.
Yeah, good one. And thinking conceptually is key. Forget rote memorization. It's about making sure the electron books balance. So first, you mentally split the overall reaction into two separate stories.
Okay.
One where iron loses an electron, that's the oxidation half. F2 plus goes to F3 plus a bi.
Simple enough.
And the other where the chromium and the dichromate ion gains electrons, that's the reduction half. Cr2O72 eventually becomes Cr3 plus a bond.
Right, so you've got the two halves separated.
Exactly. Then you balance the atoms that aren't oxygen or hydrogen first. So on the chromium side, you have Cr2O72 that needs to make two Cr3 plus ions to balance the chromium atoms.
Makes sense. Two on each side.
Then you tackle the oxygen. You balance oxygen atoms by adding water molecules. So for Cr2O72 becoming 2 Cr3 plus score, you'd need 7 water molecules on the product side.
Okay, 7H2O.
And then, assuming we're in an acidic solution, you balance the hydrogens you just added by putting H plus ions on the other side. So 14 H plus ions go on the reactant side for the dichromate reduction.
14, wow, okay. And then you get to the electrons.
Then comes the crucial part, balancing the charge by adding electrons. The iron half is easy. A2 plus loses 1 electron to become F3 plus 2, so F2 AE plus 3 plus E.
Right.
The chromium half, after you add up all the charges on both sides, needs 6 electrons added to the reactant side to balance out. So 6E plus 14H plus Cr2O72, 2Cr3 plus 7H2O.
Ah, okay. So one half loses 1 electron, the other gains 6. Not balanced yet.
Not yet. So the final balancing act is to make the electrons lost equal the electrons gained.
Yeah.
You multiply the entire half reaction by the smallest whole number needed. Here we multiply the iron half reaction by 6.
So 6Fe2 plus 6Fe3 plus 6E. Now we have 6 electrons lost and 6 electrons gained. Perfect.
Exactly. Then you just add the two adjusted half reactions together. The 6 electrons cancel out on both sides. And sometimes other things like H plus or water might cancel too, depending on the reaction.
And you end up with a fully balanced equation. 6Xe2 plus 14H plus plus Cr2O72, 6Fe3, plus Dr3, plus 7H2O. It maps the whole electron journey.
It really does. And, if the reaction happens in a basic solution, there are just a couple extra steps involving adding hydroxide ions, OH, to deal with the H plus A, but the core logic of balancing atoms and then charge remains the same. It's a really versatile method.
Okay, so once we've sort of mastered this precise electron accounting, nailing down where every electron goes, the next logical step, and maybe the most exciting part, is figuring out how to make those electrons do something useful for us.
Yes. And that brings us right to galvanic cells. You might also hear them called voltaic cells.
Right.
These are really ingenious devices. They take a redox reaction that happens spontaneously, one that wants to happen anyway, and they harness that natural electron transfer to generate a usable flow of electricity.
So instead of the electrons just swapping places directly between chemicals and maybe releasing heat?
Exactly. We cleverly separate the oxidation part and the reduction part into different compartments. And then we force the electrons to take the scenic route, traveling through an external wire to get from where they're lost to where they're gained.
Okay, here's where it gets really interesting for practical stuff. Let's break down the components. You need an anode, right? That's where the oxidation happens, the source of the electrons, where they're lost.
Correct. And then you need the cathode. That's where reduction occurs, where those electrons traveling through the wire end up being gained by something else.
And these are usually metal bars, the electrodes, and each one is sitting in a solution making up a half cell.
That's right. But here's a crucial piece. The salt bridge. You absolutely need it to keep the electrons flowing.
Why is that?
Well, think about it. As electrons leave the anode compartment, that solution starts building up positive charge, right? Because positive ions are being formed or negative ions are leaving.
Okay, yeah.
And simultaneously, the cathode compartment gains electrons, so it starts building up negative charge. This charge imbalance would immediately stop the electron flow. It creates an opposing voltage.
Ah, like a traffic jam for electrons.
Exactly. The salt bridge prevents that. It's usually a tube filled with a salt solution, like potassium nitrate, that allows ions to migrate between the two half cells. Anions, negative ions, flow towards the anode to balance the positive buildup, and cations, positive ions, flow toward the cathode to balance the negative buildup. It completes the circuit internally.
So it's like the ion traffic controller keeping the electron highway open. And then, of course, you have the external wire connecting the anode and cathode. That's the path the electrons take.
And we can measure the push behind those electrons, the electrical potential difference, with a voltmeter. It tells us the voltage of the cell.
Our sources often use the classic Daniels cell as an example. That's the one with a zinc electrode in zinc sulfate solution and a copper electrode in copper sulfate solution.
Yeah, textbook example. In that cell, zinc metal is the anode. It gets oxidized to Zn2 plus ions. And copper ions in solution are reduced to copper metal at the cathode. So electrons flow spontaneously from the zinc electrode through the wire to the copper electrode.
It's, like you said before, kind of like a waterfall, but for electrons. Water flows down because of a difference in gravitational potential energy.
And electrons flow from the anode to the cathode because of a difference in electrical potential energy between the two half cells. That difference is the cell potential, or voltage, the E cell.
And there's even a shorthand notation for these cells, isn't there? Like ZNS, ZN2 plus 1M, Cu2 plus 1M, CS.
Right. The single vertical line means a phase boundary, like between the solid zinc metal and the zinc ion solution. The double vertical line in the middle represents the salt bridge connecting the two half cells. It's a compact way to represent the whole setup.
Okay, so these cells generate a voltage. We can measure it. But how do we figure out the potential of just one half cell? You mentioned you can't really measure one in isolation.
That's the tricky part. You always need a complete circuit, a potential difference. So chemists came up with a clever solution, a universal reference point. It's called the standard hydrogen electrode, or SHE.
The SHE. Okay, what is that?
It's basically a specially prepared platinum electrode immersed in a 1 molar acid solution with hydrogen gas bubbling over it at 1 atmosphere pressure, all kept at 25 degrees Celsius. And by international agreement, this specific half-reaction 2H plus gaining 2 electrons to become H2 gas is assigned a standard reduction potential, E degrees, of exactly 0 volts.
Ah, so it's like the sea level for electrochemistry. Everything else is measured relative to it.
That's a perfect analogy. So if you want to find the standard potential of, say, the zinc half cell, Zn2 plus 2E again, you build a galvanic cell with the zinc half cell and the SHE. You measure the total voltage of that cell. Since you know the SHE is 0 volts, whatever voltage you measure for the whole cell must be due to the zinc half cell relative to hydrogen. When you do this, you find the zinc potential is -great 0.76 volts.
Negative, what does that mean?
It means zinc metal is more easily oxidized than hydrogen gas. Electrons actually flow from the zinc to the SHE in that cell. For copper, Cu2 plus 2EO, you measure plus 0.34 volts, meaning copper ions are easier to reduce than H plus ions. Electrons flow from the SHE to the copper.
Got it. So by comparing everything to the SHE, we can build up a whole table of these standard reduction potentials for different half reactions.
Exactly. And that table is incredibly powerful because now to find the standard cell potential, ED cell, for any combination of two half cells, you just look up their standard reduction potentials and use the formula. ED cell, ED cathode, E degree anode.
The potential of where reduction happens minus the potential of where oxidation happens.
Precisely. So for our Daniell cell, zinc anode, copper cathode, ED cell plus 0.34 V, nu 0.76 V, plus 1.1 V, the calculation perfectly matches the measured voltage under standard conditions.
And what's really key here, you mentioned, is the sign. A positive E to cell tells us something important.
Absolutely crucial. Yeah. A positive E degree cell under standard conditions means the reaction, as written, is spontaneous. It's product favored. It wants to happen. A negative E degree cell means the reaction is non-spontaneous in that direction. The reverse reaction is actually the spontaneous one. It's like a chemical crystal ball.
That is powerful. Just look up two numbers, subtract them, and boom, you know if the reaction goes.
There's one more important detail here about these potentials. They are intensive properties.
Intensive, meaning they don't depend on how much stuff you have, like temperature or density.
Exactly. So remember how we sometimes have to multiply a half reaction by a number, like 2 or 3, to get the electrons to balance when combining them.
Yeah, like we multiplied the iron half reaction by 6 earlier.
Right. When you do that for balancing, you absolutely do not multiply the E degree value for that half reaction. The potential is inherent to the chemical change itself, not the amount of it happening. So if you double the size of your electrodes, you don't double the voltage.
Okay, that's a common mistake to avoid. Don't multiply the volts. So this table of potentials is fantastic for predicting reactions under ideal standard conditions.
It is. But we can go further. We can actually connect electrochemistry directly to thermodynamics specifically, to the standard free energy change, AG, and the equilibrium constant, K.
Ah, bringing Gibbs free energy into it. How does that work?
There's a really important equation. Dg degree equals an NFE degrees.
Okay, break that down. Dg is the standard free energy change.
Right. N is the number of moles of electrons transferred in the balanced overall reaction. F is Faraday's constant. It's about 96,500 coulombs per mole of electrons. It's the bridge between electricity, charge, and chemistry, moles. And E degrees is our standard cell potential.
So if E degrees is positive, meaning spontaneous,
the G degrees must be negative because of the minus sign in the equation. And a negative G degrees is the thermodynamic sign of a spontaneous product-favored process. It all links together beautifully. You can also relate E degree cell directly to the equilibrium constant, K.
Okay.
The equation at 25 degrees C is approximately E degree cell, 0.0592 V log K. A large positive E degrees corresponds to a very large K, meaning the reaction goes almost to completion.
Wow. So potential, free energy, equilibrium, they're all telling the same story about spontaneity, just from different angles.
Precisely. What's fascinating here, though, is that standard conditions, 1 molar solutions, 1 at area and pressure, are useful for reference, but, they're rarely what we encounter in the real world or even in the lab sometimes.
Yeah, concentrations change as a reaction proceeds, right? A battery doesn't stay at 1 M forever.
Exactly. And that's where the Nernst equation becomes absolutely essential. It's our reality check. It lets us calculate the cell potential, E, under non-standard conditions.
Okay, so the Nernst equation isn't just some abstract formula. It's like our tool for figuring out the voltage when things aren't perfect, our GPS for real-world cells.
That's a great way to put it. The common form at 25 degrees C is E equals E degrees, 0.0592 Vn log Q.
E is the non-standard potential we want. E degrees is the standard potential we look up. N is moles of electrons. What's Q?
Q is the reaction quotient. It has the same form as the equilibrium constant K, but uses the current concentrations or pressures, not necessarily the equilibrium ones. It's a snapshot of where the reaction is right now.
Ah, okay. So how does Q affect the voltage?
Well, think about it. If Q is large, meaning you have a lot more products than reactants compared to equilibrium, log Q is positive, so you subtract a larger term from E degrees. Yeah. The actual voltage E will be lower than the standard voltage E degrees. Your battery voltage drops as the products build up.
Makes sense, as the battery runs down.
Conversely, if Q is small, mostly reactants, log Q is negative. and E actually becomes higher than E degrees.
Uh,
The equation tells us precisely how the potential changes as the reaction progresses towards equilibrium, where E becomes 0 and Q equals K.
that's incredibly useful. It explains why battery voltage isn't constant, and you mentioned pH meters.
Yeah, a typical pH meter is essentially measuring the potential of a special electrode that's sensitive to the H plus ion concentration, using the Nernst equation to relate that measured potential directly back to pH.
Brilliant. So it really lets us fine-tune and understand electron flow in real situations. And there's a clever application using just concentration differences, right? Concentration cells.
Yes, these are neat. You set up a galvanic cell using the exact same components in both half cells, say, zinc electrodes in zinc sulfate solutions, but the concentrations of the zinc ions are different in the two compartments.
So maybe 0.1 M in one and 1.0 in the other.
Exactly. Now, what's the standard cell potential, E degree cell, for this? Since the anode and cathode reactions are just the reverse of each other, Zn2 plus and Zn2 plus iodane, E degrees is actually 0.
0. But does it still generate a voltage?
It does, because the concentrations aren't standard. The Nernst equation tells us a potential exists simply due to that concentration difference. The cell will spontaneously operate in a direction that tries to equalize the concentrations oxidizing zinc in the dilute side and reducing zinc ions in the concentrated side. Electrons flow until the concentrations become equal.
That's clever. Nature doesn't like concentration differences.
And our sources highlight a really surprising application, using concentration cells to measure the tiny ion concentrations produced by sparingly soluble salts like silver cyanide, AgCN. This lets chemists determine their solubility product constant, KSP, which would be almost impossible otherwise.
Wow, measuring things you can barely dissolve.
Yeah.
Okay, so from these fundamental principles and equations, let's jump into the really tangible stuff. Batteries and fuel cells are portable power sources.
Right. So a battery is basically just one or more galvanic cells packaged together conveniently as a portable, self-contained source of direct electric current. All the reactants are sealed inside.
And we use so many different types, like the basic dry cells in, say, an old flashlight, zinc container as the anode, graphite rod cathode, and that moist paste inside, manganese dioxide and ammonium chloride.
Yep, that's the classic Leclanche cell. Produces about 1.5 volts. Then you have the alkaline batteries, which are an improvement. They use a basic potassium hydroxide, KOH electrolyte, and often powdered zinc for the anode, giving them better performance, a longer life. Still around 1.5 volts.
Okay, and then the big one for cars, the lead-acid battery, that heavy brick under the hood.
The workhorse. Usually 6 cells connected in series, each producing about 2 volts, giving you 12 volts total. Lead plates serve as the anode, and lead dioxide-coated plates are the cathode, all immersed in sulfuric acid.
And the key feature there is rechargeability, right?
Exactly. By forcing current back through the battery using your car's alternator, you reverse the chemical reactions that occurred during discharge. You regenerate the lead and lead dioxide. This is a perfect preview of electrolysis, which we'll get to.
And powering almost everything now, our phones, laptops, even EVs, lithium-ion batteries.
The game changers.
Yes.
Their big advantages are a much higher cell potential, typically around 3.4 volts or more per cell. They're incredibly lightweight because lithium is the lightest metal, and they can be recharged hundreds, even thousands of times without significant degradation.
So batteries store their energy internally. How are fuel cells different?
The key difference is that fuel cells don't store energy like batteries. They require a continuous external supply of reactants, the fuel and an oxidant, to operate. They convert chemical energy directly into electrical energy as long as the fuel is supplied.
The most common example is the hydrogen-oxygen fuel cell.
That's the classic. Hydrogen gas is fed to the anode, oxygen gas, usually from the air, cathode, and they react electrochemically to produce water and electricity, H2 plus O2 H2O.
And the big advantages there are efficiency and cleanliness.
Huge advantages. Direct electrochemical conversion is much more efficient than burning the fuel, maybe 70% efficiency, compared to maybe 40% for a good combustion engine. And the only byproduct is pure water. That's why they're used in spacecraft, providing both power and drinking water for astronauts, as our sources note.
That's just amazing. From flashlights to spacecraft, all powered by cleverly controlled electron flow.
It really is. Now, so far, we've mostly talked about spontaneous reactions that give us electricity in galvanic cells and batteries.
Right, reactions that want to happen on their own.
But what if you want to make a reaction happen that doesn't want to occur spontaneously? What if you need to force a chemical change against its natural tendency?
Like going uphill instead of downhill.
Exactly. That's where electrolysis comes in. It's essentially the opposite of a galvanic cell. You use an external source of electrical energy to drive a non-spontaneous chemical reaction.
And the setup for this is called an electrolytic cell.
Right. A prime example is the electrolysis of molten sodium chloride. Solid NaCl won't conduct electricity, but if you melt it at high temperatures, the Na plus and Cl ions are free to move.
Okay.
If you then apply a sufficiently high voltage, our sources estimate around 4 volts across 2 inert electrodes immersed in the molten salt, you can force the non-spontaneous reaction to happen. Sodium ions, Na+, are forced to accept electrons at the cathode, becoming molten sodium metal. Chloride ions, Cl, are forced to give up electrons at the anode, forming chlorine gas.
So you're literally using electricity to break down table salt into highly reactive sodium metal and poisonous chlorine gas, things that would never happen on their own.
Precisely. It's a major industrial process for producing both sodium and chlorine. You can also electrolyze water. Pure water doesn't conduct well, but if you add an electrolyte like sulfuric acid,
you can force it to split into hydrogen gas and oxygen gas.
yep, H2 forms at the cathode, O2 at the anode. It's a way to produce very pure hydrogen and oxygen, potentially using renewable electricity sources.
Now, what about electrolyzing aqueous sodium chloride? Salt water. That seems more complicated.
It is, because now you have water molecules competing with the Na plus and Cl ions at the electrodes. Water can also be oxidized to O2 or reduced to H2.
So which reaction wins?
It depends on the potentials, but also sometimes on a phenomenon called overvoltage. This is where the actual voltage required to make a specific reaction happen at a reasonable rate on a particular electrode surface is higher than the theoretically calculated standard potential.
Like an extra energy barrier you have to overcome?
Kind of. It can be due to slow steps in the reaction mechanism at the electrode surface. In the case of aqueous NaCl, overvoltage effects, particularly for oxygen formation, mean that even though thermodynamically water should be oxidized more easily than chloride, kinetically, it's often easier to produce chlorine gas at the anode.
Ah, so kinetics can sometimes override thermodynamics in electrolysis. Interesting.
And beyond just making reactions happen, electrolysis has crucial quantitative applications. This goes back to Michael Faraday's brilliant work.
Faraday again? What did he figure out?
He discovered that the amount of substance produced or consumed during electrolysis is directly proportional to the total amount of electrical charge passed through the cell. It's a direct stoichiometric link.
So more electricity equals more product.
Exactly, and we can calculate it precisely. Current is charge per time. Amperes cols is second.
Yeah.
So if you know the current applied and the time it runs for, you can find the total charge in coulombs. Charge, current x time.
Okay.
Then, using Faraday's constant, F 96,500 coulombs per mole of electrons, you convert the total charge into the number of moles of electrons that were transferred.
Coulombs to moles of electrons. Got it.
And finally, you use the stoichiometry from the balanced half reaction, how many electrons are needed to produce 1 mole of your product to convert moles of electrons into moles of product. From there, you can easily get mass or volume.
Wow. So you can calculate exactly how much magnesium metal you'll get from electrolyzing molten MgCl2 for a certain time at a certain current.
Absolutely. Or how much chlorine gas you'd produce. Industries use these calculations constantly for electroplating, refining metals like aluminum and copper, and producing key chemicals. It's literally building materials with electricity based on precise counting of electrons.
Incredible. Okay. One last major area our sources cover, and it's kind of the unwanted side of electrochemistry. Corrosion.
Ah, yes, the bane of many metal objects. Corrosion is basically the deterioration of a metal through an undesirable electrochemical process. Rust on iron is the most familiar example, but you also see tarnish on silver, or that green patina on copper roofs and statues.
So rust isn't just iron going bad, it's actually an electrochemical cell.
It is. Specifically for iron rusting, you need both oxygen and water. What happens is that different parts of the iron surface act as the anode and cathode of a tiny, spontaneous galvanic cell.
How does that work?
At an anodic site, often a spot with impurities or stress, iron metal is oxidized, Fe2 plus Aq plus 2. The electrons released travel through the metal itself to a cathodic site.
Okay, and what happens at the cathode?
At the cathode, which needs access to both oxygen and water, oxygen is reduced, usually to water. O2G plus 4H plus Aq plus 4E to H2OL. The H plus ions are typically available from dissolved CO2 in the water, forming carbonic acid.
And the Fe2 plus ions.
They migrate through the water layer and react further with oxygen and water to form the hydrated iron 3 oxide Fe2O3 H2O, which is the flaky reddish-brown stuff we actually see as rust.
And this explains why salt water makes things rust faster.
Definitely. The dissolved salt ions make the water a much better conductor of electricity, which helps complete the internal circuit of that tiny corrosion cell, accelerating the whole process.
So it's a mini galvanic cell destroying the metal. Why don't all metals corrode like that? Like aluminum seems pretty resistant.
That's a great point. Some metals, like aluminum, react with oxygen very quickly, but they form a very thin, tough, non-porous layer of metal oxide, and in aluminum's case, Al2O3. This oxide layer adheres tightly to the surface and acts like a protective shield, preventing further oxygen and water from reaching the metal underneath. Iron oxide, rust, is porous and flaky, so it doesn't protect the underlying iron.
Ah, the nature of the oxide layer is key. So how do we fight back against corrosion?
We have several strategies. The simplest is just coatings, paint, plastic, grease that act as a physical barrier between the metal and the environment. But if the coating gets scratched,
The corrosion can start underneath. Right.
another approach is using alloys. Stainless steel is a perfect example. Adding chromium to iron allows a thin protective layer of chromium oxide to form on the surface, similar to aluminum oxide, shielding the iron.
Smart, mixing metals for protection.
But perhaps the cleverest method, electrochemically speaking, is cathodic protection.
Cathodic protection, making the thing you want to protect the cathode.
Exactly. Remember, oxidation, corrosion, happens at the anode. So if you can force your valuable metal structure, say a steel pipeline or a ship's hull, to be the cathode in a galvanic cell, it won't corrode.
How do you do that?
You connect it electrically to a different metal that is more easily oxidized, a sacrificial anode. This other metal corrodes instead, sacrificing itself to protect the steel. You just have to replace the sacrificial anode periodically.
Like zinc blocks on ship hulls.
Precisely. Zinc is more easily oxidized than iron. Its reduction potential is more negative. Galvanization coating iron or steel with zinc works on the same principle. Even if the zinc coating gets scratched, the exposed zinc corrodes preferentially, protecting the iron nearby. It's electrochemical sacrifice.
That's really ingenious, using electrochemistry to fight electrochemistry.
It really is. So you see, from balancing equations to powering devices, building materials, and even understanding and preventing decay, it all comes down to this intricate dance of electrons.
It truly is all about controlling and understanding that electron flow, whether we want to harness it for power, use it to create something new, or stop it from destroying something valuable.
So the next time you plug in your phone, or you notice rust starting on an old fence, or maybe even just think about how your own body uses chemical reactions to generate the energy for, well, thinking about electrochemistry. You'll know it's all part of this incredible, intricate dance of electrons governed by these principles we've talked about.
It makes you wonder what other everyday processes out there might be hidden electrochemical reactions just waiting for us to uncover them. Keep exploring, everyone, and we'll keep diving deep.